I'm Carmela. I'm the biomedical engineer and the project lead.
Hey, I'm Daniel. I'm the electrical engineer of the team.
I'm Alec. I'm a mechanical engineer.
And I'm Michael, and I'm a biosystems engineer.
Oh, hey, I'm Mohato Sayar, purchasing lead for this team and the electrical engineer.
So what is a MediBrick 2000? The MediBrick 2000 is a modular biomedical sensor board meant for biomedical engineers to use in their laboratory or classroom session. It has an ECG, a pulse ox, an impedance, a digital stethoscope, and a temperature sensor. This device is cost-effective, user-friendly, and it's easy to replicate and repair.
Tell me, why is the MediBrick important?
The MediBrick is important because it will allow engineering students to take, record, and analyze real physiological data with a low-cost system that any university can afford to buy many of.
Hey, Daniel. Do you know what impact does the MediBrick 2000 have in society and the environment?
Yeah, actually I do. The MediBrick 2000 is a low-cost device, so any student from the biomed department can access to a comprehensive sensor array. And also it's an open source device, so it promotes collaboration, customization, and anyone can actually expand the project. So since it's easy to replicate and easy to repair, anyone in the microcontroller community can contribute to it.
Oh, that's very interesting. During the development of the device, we went through many different engineering processes, such as soldering, PCB design, and coding. Also debugging microcontrollers, and hardware development, 3D printing, as well as micro soldering. And of course, we do the most exciting part, paperwork.
So for our project, the system requirements are that the system is accurate with low signal noise, it is safe mechanically, chemically, and electrically, it is small enough to fit on a desk, it is cost effective, and that it is user-friendly with the ability to record, save, and later analyze data from the GUI.
For this project, we conducted our research for similar devices in the market that can perform several physiological measurements at the same time, but the problem is that they were exceedingly expensive. Also, we conducted a research about similar projects for each one of the different sensors that were efficient, accurate, and low cost. And also we used some research papers to use as a reference.
Multiple engineering standards were also applied during the development of this project. These standards are mostly for electrical safety, medical devices, and privacy protection. During the early stages of the project, we also contacted the IRB since we do require measuring multiple individuals. It was later confirmed that we are allowed to do so since it is meant for educational purposes.
So, for overall system function, each sensor has its own PCB and probe, which it will use to sense different physiological data. That data will then be processed by each sensor's ESP before being sent off to the central receiver and to the GUI to display. And when you want to charge each sensor housing, all you need to do is simply plug it back into the central housing.
So for the first sensor, we have the ECG. This can be used to measure the electrical potential of the heart. As we can see, the signal comes from these wires, which will then be sent through a preamplifier board, which is then sent through the ESP, which has a digital filter, and then can be wirelessly sent to our receiver, and then we can see in our GUI.
So here we have the temperature sensor. It operates using a thermistor, which changes its resistance due to temperature. We have a Wheatstone bridge in here that measures the voltage across the thermistor and compares it with a baseline. And then using analog and digital filters on its way to the ESP, calculates the temperature before sending it off to the receiver and to the GUI.
So this is the pulse oxy sensor. It measures SpO2 and the heart rate by detecting the absorbance of IR and red value wavelengths and sending it to the main IC chip, which is then digitized and sent to the ESP into a algorithm and then sent to the master ESP and sent to the GUI displaying the necessary data.
So for our next sensor, we have the impedance sensor. So this sensor can be used to measure your body impedance, body fat percentage, and water composition. For this sensor, we created our own circuitry. It works by sending an electrical signal through the excite plug, which will then go back to the measure plug, and this information will then go into the impedance analyzer chip, which will then be sent to the ESP, wirelessly connected to our receiver, and then be sent into our GUI.
This is a digital stethoscope model. As you can see, it's pretty simple, but its real beauty lies in its simplicity. So it all starts in the stethoscope, in the actual stethoscope that is connected to the microphone. Then the signal goes to a preamplification stage, then it has an analog filter, as you can see here, then it gets digitized, and it finally sent to the microcontroller. In the ESP, we filtered the signal once again with a digital bandpass filter, and finally the signal is sent to the GUI wirelessly.
Here we are going to be talking about the casing and housing for the modules. Here we have the sensor, as well as vents for heat disposition, the button slot, spot for the OLED, and the charging slot. On the inside, we have here where the ESP will rest. It will be charged by the battery, which will sit in here. You see the button slot has a bit of a backing so that it can be pushed into without much issue. And you see that the charging station connects directly up, leads directly up with the ESP. For the top portion, we have where the PCB will rest. It has feet for that to rest onto so it doesn't directly touch the majority of the plastic, causing great heating. And more screw holes so it can be threaded, and it is lined up right up with the sensor module. And here we have the charging station. It has the mentioned bucket where the sensors will rest into. The blocks themselves will rest onto here with little charging ports so that it may sit upon. It has the outlet. It'll plug into an outlet with this cable that is resting within inside of it, and has a little slot right here for the receiver, the master of the system, to be able to rest into.
The deliverables for this project are one complete system, being the five sensors and all of the housings, as well as the documentation required to operate and build the system, including STL files, codes, and PCB files.
One of the problems we have throughout these 2 semesters was the integration of the entire system. At the beginning, the sponsor wanted to use Raspberry Pi as the main microcontroller of the device. However, it presented several issues related to modularity and electrical safety. Instead, we proposed him and eventually convinced him to use the ESP32S3. Then another challenge that we faced was the research of the parts, especially with the trade-off between the price and the quality or accuracy of the parts. We solved this problem by creating circuitry from scratch, applying several analog and digital filters, and throughout analysis that improved the quality of our signals.
Here we have the verification summary for our system requirements. The uncompleted tests will be completed the week before FAR. For the sensor quality tests, we've completed all of them except for skin impedance accuracy. For the general system tests, we've completed all of them except for the final weight requirement. For the safety requirements, we've completed all of them and proved that the system is safe to operate. For the computer communications tests, we are working to complete the last few, being that the system can save data from each sensor and communicate with each sensor to display data on the GUI.
So this concludes the presentation for our project, the MediBrick 2000, and we would like to thank the following people and organizations for making this project possible.
We would like to thank Dr. Utzinger, our sponsor, for his trust in us in this project, while also being encouraging and happy. We appreciate it.
We also want to thank Mr. Larrymore, our mentor, for his lessons, advices, and support throughout these 2 semesters.
We'd also like to thank the Salter Lab for allowing us their space and their tools, as well as the Engineering Design Center for their 3D printers and meeting spaces.
We would like to thank the Craig M. Berge Engineering Design Program for bringing us together to work on this project and for funding it.
And finally, we would like to thank you for watching our presentation.
Let's go.
Yeah! Yeah!